2, 1. All right, so welcome to the introduction to exponential probability distribution. My assumption is that you are taking data management or some kind of statistics, and it's completely introductory. So you haven't seen this before. And my goal will be to try to introduce you to this exponential probability distribution. And it is from the viewpoint of continuous probability distributions and continuous probability density functions. So now, what is this exponential probability distribution? Well, the idea behind having an exponential probability distribution comes to the application towards predicting the length of time until an event actually happens. So it turns out that when you do have, a random variable, which is basically time, kind of length of times, it doesn't always have to be, but it's best explained through that. You want to be able to see what's the probability, that some event, so maybe you're calling a customer service line, that your call is going to be answered within 5 minutes, within 10 minutes. So in terms of maybe your waiting time, or maybe you're waiting for what will happen or how long does it take until maybe there's a malfunction, all right, in some factory. So we want to be able to model these, and we model them sometimes by exponential probability distributions. So the key variable for us in here will be, I will be assuming that our x, or basically our random variable, is going to be the length of time. Now, before I jump in and I present to you what that exponential probability density function looks like, let's kind of take a step back and think about when you were studying discrete probability distributions. So one of the discrete probability distributions that you studied, was with respect to the geometric distribution. And I'll put up a link up above there because I think it's worthwhile if you haven't touched on that, or you have forgotten it. So if you go back, what this was all about was how long will we have to wait, so this concept of waiting, before we have a successful outcome. And now that could be just flipping, a coin. And you can imagine that a successful outcome maybe is seeing a heads. So how many times will we have to flip before we see a heads? And that is based all on probabilities. And therefore, so what we ended up doing was, so our random variable is going to be actually the unsuccessful, events that happen. So this is unsuccesses that we had. And this just gave us, so the P, in here that you see, the little p, is the probability, of seeing a success. So if it was heads, it would be 50%, and then tails would be 50%. But it doesn't have to be heads or tails. It could be any event, that you want. And what we wanted to do is, what we were saying is that we had right here, well, if I don't wait, so if x is equal to 0, if I right away get a successful event, then my probability was just simply equal to p, whatever it might be. Let's say for our heads, event would have been 0.5. Now, what if I had to wait, right? What if I threw and then basically I had one unsuccessful event? So I had a tails and then I had a heads. So in that case, what we would have done is we would have said, that's 1 minus p multiplied by p. Now, what if you had two unsuccessful events? Then again, it would have been 1 minus p times 1 minus p, and then we had a success. And so on, we would do this, trying to see how many unsuccessful events we had before a success happened. And that gave us the probabilities. We could sum up all of these probabilities and say what they were. Let's say within 3 tosses of a coin, what's the probability that I'm going to see, my heads? And I could have just added them up. And when we were doing this, I also graphed this out, on Desmos. So I'm going to do that for you again. So let me bring up Desmos here. So I'm going to bring it out so that I have it here on the side. And I just want to refresh your mind, on this, so with respect to that. So here, what I'm going to do is I said, okay, so so here's my function. So let's say P, all right, so this is 1 minus P, all right, to the X times P. Now I'm going to put P is a slider, all right, so it has to be some probabilities between 0 and 1. So let's say we had 0.5, and I'm also going to restrict, so let's say X has to be greater or equal to 0, right, because it can't be negative in this case. So here is our function right here that we had. But these were discrete events. So you either had 0 on successes, right? So you had a success on the first try, okay? You had a success maybe on the second try, meaning 1 unsuccessful event, and so on. So really, it wasn't a continuous, exponential decaying down. It was, so if I put this in here, so I'm going to define a list here. Let's say maybe only up to 6, all right? And now I could have graphed this out. So I could have said, okay, let me graph this out. Let me substitute this back in. And really, we would only be seeing that, right? So the more flips you have, the probabilities are decreasing, right? Because of the fact that it's actually hard to be unsuccessful, on so many consecutive events. But if I bring back this, now it becomes continuous, right? Now, it wouldn't make sense for a successful event, so a failure and a success, but since we're studying probabilities, or the probability distributions for continuous now, and the variable is, let's say, length of time, right? What if this was based on the length of time? Then you can clearly see that, well, this looks like a nice exponential going down within here. And that's exactly true. So the waiting time, because we no longer have events where they're just a flip of a coin. Now we're waiting, and that waiting could be a minute, could be half a minute, could be 10 seconds, 5 seconds. It could be anything. So it should kind of look like an exponential as we are waiting for a success to happen, for an event to actually occur. And that's all what an exponential probability distribution actually is. So if I go back here, so if I remove this, I have written out what the actual continuous probability density function looks like. So here I like to write it as f of x, all right? And then I have this lambda. I'm going to explain what this means so that you just kind of see it. Now, this e, right? So that's your Euler's number, It is used for exponentials, and you have been introduced to it in grade 11 in functions. So I'm assuming that you've had this. Now, if you've forgotten or you don't know where it comes from, I actually kind of derived where it came from, and it is used heavily in mathematics and in sciences because it's a very convenient number. It is an irrational number, which is 2.71. Now, it continues on. It goes on forever. If you want to see the derivation, look up above, But it is a number. It's an irrational number that we use, and we actually use it for these exponential probability distributions. So now, what is this lambda that we have? So this lambda that we see in here. Now, it doesn't have to be lambda. Maybe your teachers will use some other constant variable, all right? But I'm using lambda, and what this means is that lambda is equal to, 1 divided by mu. Now, mu is the mean, so you will remember the mean from statistics. So you have mean, medium, and mode. So it's basically an average. And what it represents is how long, on average, so that's why the mean, one event takes place. And if you are thinking about what the lambda means, that means that this tells us this is a unit of time. So you can imagine it's either, now a unit of time could be 1 minute, it could be 1 second, it could be 1 hour, it could be 1 day. So that's a unit of time. So this is a unit of time, and it could be, again, it could be second, it could be a minute. It depends on the question. All right, so you'll see that. And now what this is saying, that if you try to explain this, well, this means that, for instance, if our unit of time was 1 minute and our mean, okay, let's say was 20 seconds. So you were waiting 20 seconds. Now, 20 seconds is 1/3 of a minute. So what you would have is you would say 1 minute, 20 seconds is 1/3 of a minute. So what this is telling you, that lambda would be that there are 3 events that happen in 1 unit of time. So that's what lambda is. Lambda is basically telling us how many events happen per a unit of time. Now, if the event takes place, and let's say it was 2 minutes, then we on average would have seen only 0.5. So our lambda would have been 0.5 events, because 1 minute divided by 2 minutes is a half. Okay, so that's what lambda is. Lambda is just how many of these events are occurring per whatever unit of time that you have chosen. And that lambda appears in 2 places. Okay, it appears here and here. Now, the negative symbol occurs because, as you saw in the discrete, you notice that we have an exponential which is decaying. And a negative, as you know, is a decaying exponential. So that decaying exponential basically will look exactly like this. It's going to start somewhere, and it's going to start to decay over time, which means that the probabilities as time goes further and further should be lower and lower, right? And they should be stacked up in the beginning. So that's what that actually represents. So now you can certainly derive, like, why the E, right? Why using this irrational number 2.71 to try to model. The lambda makes sense, the mean makes sense, right? But why does it look like that? Well, that just has come out, okay? And you would have to know a little bit more information, but for introductory purposes, you can assume that you can model waiting times related to probabilities by this probability density function. And remember, it is a probability density function. So you can't say that the probability of waiting 2 minutes is a number. No, no, no. Because remember, from studying continuous probability distributions, it has to be an interval that you're trying to find out what the probability is over that interval. So you can certainly say, what is the probability, okay, of, let's say, my x, okay, being less than 5 minutes. So if I'm waiting for an event to happen, what would have been the probability, okay, for me to see that event happen in under 5 minutes? And that you can calculate, because you would do, okay, what you would have is, here is your vertical axis, here is your horizontal axis. So this is really time, right? So that my x right here would have been time. Now it starts somewhere else, okay? So starts right here, which means that this has to be for greater or equal to 0 right here. And then it's going to look like this. It's going to just sway all the way down. And that time, so let's say if this was 5 minutes, and you wanted to find out what the probability would have been, you would have to find, remember, from the continuous, so understanding continuous probability distributions, that you have to find the area under the curve to find the probability. And if you've forgotten about that, okay, I did the introduction, I'll put it up above there for the continuous probability distributions. And that now gives you, that would give you that probability. And that probability, so remember, we use summation like this when it's discrete events. But from that video, we do not use this because this is for discrete. We use an S, which is actually an integral, okay, in mathematics, which you'll study at some point. And now this would have been an integral between, so starting at 0 and going, 5 minutes right here. And then you would have put that you want to know the sum across this entire function. So I'm going to copy this, okay, and I'm going to place that. So you want to find the sum across all the values, right? And now you say, how the heck am I going to do that? If it's something simple, if the probability density function is, uniform, constant, then it's easy to find the area under the curve. But here, how will we find the area under the curve, okay, in order to find these probabilities, right? And then what if the probabilities maybe were between, 2 different points? Maybe they were from here to here, and you had to find that. Well, we can approximate it for this function. So if you break this down into several, let's say you did it every minute, so 1, this would have been 2, 3, and 4, okay, you can actually break it down as so. And if I take one of these pieces out, okay, what you notice is that it very much approximates basically like a trapezoid, but it's a very nice trapezoid with some height. So let's say this is height 1, this is height 2, and you can easily break this down into a rectangle and then a little triangle. So the base right here, so in our case it's 1 minute, but this would have been any base you like, and you do typically make them smaller. And then you can find out what the area of this is. Now the area of something like this is, as I mentioned, it's the rectangle plus the little triangle, okay? And you can find that this is nothing else but simply your base, right, which shouldn't surprise you. And then it is 1/2 of your height 1 plus your height 2, which really is just the middle point. So that is the area, okay, that we have. And for this, so if I do this right like this, really what you're doing is, okay, you're approximating it like this, all right? And that is your base, and then height 1 plus height 2, and you might remember that from geometry. So now we can find what this is, we can find what this is, we can find what this is, or any of these triangles that we carry. And if you make the triangles small enough, so basically when the width of them approaches and gets closer and closer to 0, it gets smaller and smaller, then this is exactly what you're doing right here. Right? But you don't want to have 100 of them, so we typically approximate only a few, okay, and get some kind of a approximation in terms of probabilities for this. Now, let me just show you on an example, okay, what this would look like so that you can get an understanding, okay, in terms of these probabilities and how to break them down with these wait times. So here I prepared an example for you. So let's imagine the average wait time when calling customer service at a bank was 3 minutes. So that means they answer their calls every 3 minutes on average. Okay, on average is different than, uniformly answering it every 3 minutes. So on average, it's 3 minutes. Again, I put here wishful thinking, but let's just assume. So now it asks us, what is the probability that your call will be answered within 6 minutes? Assuming wait times are approximated by the exponential probability distribution. Okay, so now we can talk about this entire thing. So for instance, so here is, okay, our probability density function. So this is f, okay, x, okay, so I'm going to do that right there. Now, my lambda is equal to 1 over the mean, which now in this case is, okay, the mean is 3 minutes. So this is 1 over 3. So my unit of time, I'm going to assume it's minutes. All right. So my lambda is 1 over 3. So that's what I have right there. So this function is 1 over 3 e to the exponent of 1 over 3x. Now for x, you can literally put little t because it's time, but I'll keep it x for the moment. So that is my exponential probability distribution. And it is a density function. Okay, this doesn't tell us the probability, it tells us the probability densities that we have across. So now I can graph this out. So I'm going to just simultaneously be graphing it as I'm going along just to show you. So here, okay, so let me just get rid of, okay, this. All right. And now I'm going to graph this out. So I'm going to say f of x, okay, is equal to, and I have 1 over 3. So this is going to be 1 over 3 times, okay, so e to the exponent of negative, again, it's 1 over 3 x. Okay, now I do have to assume, so I'm going to put restraints on this. Now this is greater or equal to 0. So I've just graphed this out. So that's my probability distribution. So that's what it would look like. So those are the times. My x-axis is time. So you can see that probability density. So if it's, as it's going through, right here in 1 minute, 2 minutes, 3 minutes, or anywhere in between, we can find out. Now, what they ask us here is they ask us, what is the probability that our call, okay, is answered within 6 minutes? So what we want, okay, so 6 minutes. Now I'm going to, okay, let's kind of cheat this. So 6 minutes right there. Okay, let me do that right here, and I can see that. I'm going to take a snapshot of this just so that I can use it within. So here is 6 minutes. Here, I'm going to do that. Okay, perfect. Let me make it even smaller. All right, done. So save it. Let's put it into our file. I'm going to come back to decimals just a moment. So all photos. So let me put that in here. Okay. So I have that. Now, they're asking us the following. They're saying, what is the probability, okay, that we have, this is going to be 6 minutes, right? Right here. Well, 6 minutes is right there. So what I have to do now is, okay, I have to find the area under this curve to find out my probability. That's what I have to do. Okay, so now I'm going to remove this just so that it's clear. So what I will do is, now I have to approximate this, because what I'm really doing is I'm trying to find the sum across all of those, okay, little points all the way across from 0 to 6. So I'm going from 0 to 6, okay, of this function. Okay, so f of x right there. And now within here, so I don't want to, make it too challenging for myself, but what I will do is I will approximate them. Okay, so for instance, in this case, so I will have something like this. All right, so here is my first approximation. So I can find the area under this point. Okay, now I'm going to go from here to here. Okay, and then close it down. This is the second one. And then again, so I'm going to just continue this, okay, as here. So this is going to be my third. So this is going to be my fourth, all right, and so on. So I'm going to find these out, okay, all the way through. So I have in total, well, this one doesn't want to work for me very well here. That's all right. Let's try it like this, 5, and then 6. And now, if I sum up, okay, all of these, then I will get this probability, right? Because it is my probability density function, so I have to sum up the area under the curve to be able to obtain those probabilities. Now, of course, this is going to take a bit of time, but I'm just going to show you on one of them. So if I would take the first one, so right here, so it's going to look something like that. All right, like this and like that. Now I can obtain, so these are 1 minute, okay, because I chunked them down into 1 minute intervals. You can chunk them down into anything else that you want. I mean, I could have approximated it and made 2 minutes, right? Okay, so I would have had only 3 pieces to calculate, but it would have been as good of an approximation. This is going to be a pretty decent approximation that we will get. So this is that first one. So as I said, to find this out, so I need the base. I need to know whatever this height is right here. And I need to know whatever this height is right here. But those are not very hard to find. And since I do have, decimals, I can actually find and calculate it. So this would have been at 0, f at 0, and then f at 1, right? And then I'm calculating this throughout. So that's what I'm trying to find. So I can use a calculator and my exponential function there. But since I have decimals already, I'm going to put it on the side. Okay, so let's take a look and see. So f at 0, okay, so that's obviously because it's 0, so that means e to the 0 would have been 1, so that's 1/3. So this is just 1/3. And then f at 1, so notice it gives me that answer. So I'm going to just approximate it 0.2388, right? 4, whatever that is there, so on. So that's my height. So now I have to get the area. So the base, so this is going to be 1/2 one of the heights plus the other. So 2, 3, 8, so on. Times the base, which is 1 minute. So that's times 1. And that is my area under the curve. So what is that equal to? So let's put that in here. So it's going to be f at 0 plus f at 1, right, times 1. So that's my result. Okay, so I have 0, so this is going to be 0.286, approximately 1. And that is the area under the first one. Now I have to do that for all of them. And you would say, wow, it's a lot of work. Yeah, you're correct. It's going to be a lot of work. Okay, so I'm going to do that in fast forward fashion so that you see these. I'm going to call this A1, and then I'm going to do it for all the other ones as well. Okay, I'll be right back. All right, so welcome back. What I ended up doing was I just defined my area. So you'll see that on decimals where it says it's on the 5th line of decimals. So it's A and then brackets X comma Y, and then I put 0.5, okay, X plus Y. So that's basically my height 1, height 2, and then it's multiplying 1. So, so here, because that is my width, so my base. Okay, so now that I have that, and then what I ended up doing is I just substituted, so the points, right, the 2 points in here, and that gave me all the different areas. Now what I have to do in between all of them is now I have to add all of them up. So I can add all of these up. Okay, so starting from the first one, so 1, 2, 3, 4, 5, 6, and when I add all of them up, okay, I'll get my answer. So my total area under the curve is equal to, and then so adding all of these up, so I'll be right back with that. All right, so there you go. So that means in decimal, so what we have, so right here, so that was my answer. If I go all the way in here, you see this, that I just added all of them up together. Okay, so those 6 trapezoids that I had in there. So that's great, okay, and it gives me basically the area under the curve, which is 0.873. So what it means is that I have about a probability of 87% of my call being answered within the 6 minutes if the average wait time is about 3 minutes. So it's pretty high. It's not going to be, remember, mean doesn't necessarily guarantee you something, but this gives me the probability. Now, you could have asked any interval you wanted. You could have said, what's the probability that I will wait between 4 minutes and 10 minutes? And then you would have to do the same thing between those, and you have to find the area under the curve there. Now, these summations, so what I highlighted here for you, this right here, Desmos actually does this for you, and it does the perfect approximation. Again, if you get into calculus and then later on you start doing integrals, which they're not typically done in high school anymore, it will depend on which high school you go to. But if you take that in universities, you will learn about this summation because it becomes very important, right? So, and it's called integration, right? Because it's on a continuous function, so we're just integrating. We're not just summing up elements. So that summation across that area under the curve in here, so I'm going to, I'll cheat here a little bit, So I have my f of x already, Now in here, I'm going to pop out, decimals. If you go to functions, you can scroll through, depends, where you, and here it is, you'll notice calculus, and it has that integral sign. So it's the summation sign. So it looks like this. Now, for our, what we started is we went from 0 and we went all the way up to, so we're going up to 6. This is of f of x, so that's the function that we want, so I defined it. Now, when you do an integral, you want to know what these bases are. So when you are doing that in calculus, so that little area, because as you keep making these smaller and smaller, all right, so here we had it as 1, right? The base was 1, but you keep making them smaller and smaller, and you basically are going to have 100 of them, 1,000 of them, 1,000,000 of them, because you're going to just make that area smaller and smaller. So the distance between here and here, we call this dx. It's the small little interval, and you do have to put that in here in decimals, because if you don't put dx, then it doesn't know that you want it over the smallest kind of base possible. And if you hit this out, all right, so within here, let me just take a look and just make sure. You need something on both sides of the, so this is, so here, there you go. You can remove that, I guess. You don't have the multiplication, it's just dx. And notice that it's summed up for us. So we got 0.87, and the correct value is 0.86466. So look how close our approximation was when we had it, the base was minute. If you made it half a minute, or a third of a minute, or quarter of a minute, that's what you're doing with that little dx. You're making it smaller and smaller. It would have gotten better and better. But now you do have tools that for most functions will actually integrate for you. It will find the area under the curve for you. But I'm sure that when you're doing this for the first time, they will want you to approximate by these, areas where you can calculate. And to be honest with you, especially universities, no one has an integration tool or decimals, so we do approximate a lot. Okay, I think this is more than enough. I hope that it gives you a sense of what this exponential probability distribution is, how to find it, how to calculate it, how to apply it to an example. Thanks for watching. We'll see you in a future video. Bye, everybody.